Exponential random variables, some of the very best random variables around. We'll say that x is distributed exponential with mean 1 over lambda, or we might write simply that x is distributed exponential with this parameter, lambda, if its density function looks like a visit. Okay, lambda times e to the negative lambda t times the indicator that t is greater than or equal to 0. I've used t here instead of x simply because oftentimes we want to think of exponential random variables as modeling the times between events. Okay, so maybe t for time. Okay, this is a common use for that, and there's a very good reason why we'll get to in a little while when we talk about the memoryless property. But for now, you might note that if you graphed this, the exponential density, it would look something like this. It's supported by the non-negative real half-line. Okay, it's 0 down here, and then it comes down like that. Okay. Hey, let's get the CDF, the cumulative distribution function, for this guy. This is going to be useful to us here in a minute. So again, I'm going to keep t as my dummy variable because oftentimes we think of this as modeling time, and so maybe I'll remember that this is defined to be the probability that x is less than or equal to t. All right? Okay. So then this will be, I guess, all I need to do here is put in, go from negative infinity up to t, and then put in my density function, right? Lambda, e to the negative lambda, and let's use a different variable there now since I'm going to integrate this guy out, and I want this ultimately to be a function of t, which appears up here in the limit of the integral sign. And I'll get that indicator function there. Need x greater than or equal to 0. I'm integrating with respect to x, right? Okay. So actually, this then I can just write as the integral from 0 to t, really, lambda e to the negative lambda x dx, and then the whole thing times the indicator function of t greater than or equal to 0, so that this indicator function is really outside of that integral now. It's okay. You should convince yourself that this is in fact a legal move. Okay. So now, what is that going to look like? Well, I'll have that lambda can come out of the integral sign there, and I'll just be left with the limit as the limit as x goes up to t of negative e to the negative lambda x over lambda minus the limit as x goes to 0 of negative e to the negative lambda x over lambda. Okay, and then times that indicator function stuff that I'm out of room here, but it's, it's this. Okay. So let's see. I can cancel some lambdas here, right, like that, right? And then I'm just going to be left with, let's see. Gosh, it's just 1 minus e to the negative lambda t times that indicator function of t being at least 0. Okay. So that's the CDF for an exponential random variable. Here's something really, really important. This may be the most important thing you ever learn in your life. Okay? Un hecho muy importante. Exponential random variables are the only continuous ones with the memoryless property. They're the only continuous random variables with the memoryless property. So again, I'm going to think about these exponential random variables as modeling the inter-event times of something of interest. Let's say times between bus arrivals. Okay, you're waiting at a bus stop. And a buzz comes by, let's say, at time 0. Now, you're interested in the time until the next bus arrives. So you wait, 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 and then at time t, you check your watch. What time is it? It's time t. The time is t. Okay, this is a t. Now, the question is, what's the distribution of the total time until the next bus arrives from time 0 until time, this time over here, time t plus s, given that it has not yet occurred in this time interval? Turns out the distribution is the same as it was in the beginning. It's the same as you sort of, the remaining time sort of, the distribution sort of gets a fresh start. It's the same as the chance that you just, you might as well set your watch back to 0, and the chance is the same as it being greater than s, okay, greater than this much. Okay, so it turns out that exponential random variables are the only continuous ones that have this property, and that geometric random variables are the only discrete random variables with this property. That's right, geometric random variables are the only discrete random variables with the memoryless property. Now, so this makes exponentials and geometrics very, very special. Okay, they're very, very special. And in fact, if you think about it, exponentials and geometrics seem to sort of model the same thing, right? Geometrics model time until the first success, right? When you do trial after trial after trial after trial after trial in discrete time, sort of. On the other hand, exponential random variables model the time until the first success, but in continuous time. That makes sense? So in fact, and we'll see this later on when we talk more about moment-generating functions, but you can actually view exponential random variables as special limits of geometric random variables. If you take the success probability going down to 0 in a certain way, then geometrics begin to approach exponential random variables. Okay? So I'm going to prove that, in fact, that exponential random variables have the memoryless property. I'm not going to prove that they are the unique continuous ones that do. I'll leave that to you if you like. But I am going to prove that they have the memoryless property. The proof is pretty easy. So again, x is distributed exponential lambda, okay, which means that the density function, for it is lambda e to the negative lambda t times the indicator that t is at least 0, and also the CDF, right? The cumulative distribution function turns out to be 1 minus e to the negative lambda t times 1 if t is at least 0. We already worked that out. It's not an equal sign. Okay, there we go. All right, so we'll just keep those things in mind. So what I want to do is to prove that the memoryless property holds for exponentials. So I'm going to start with the left-hand side of what the memoryless property says. It says that the chance that x exceeds t plus s, given it exceeds t. Well, here's what I'm going to do. I'm going to use the definition of conditional probability here. All right, because that's exactly what that is. It's a conditional probability. It's the chance that x exceeds t plus s and x exceeds t over the chance that x exceeds t. All right. It's the chance of A and B over the chance of B. Right. Now, take a look at these two events in here. One actually implies the other. Let me draw that little picture there that we had before. If I have my timeline here, 0, t, here's t plus s, right? This much is s, this much is t. Then note that x being greater than t plus s actually implies that x is greater than t, right? So, in fact, if I look at this, the intersection of these two events up here, it's really, the intersection of these two events is really, it's really the same thing as x being greater than t plus s, right? In order for both of these to happen, this one must happen, right? So divide that by the chance that x is at least is greater than t. Okay, yeah. So this is, so I reasoned through that step by drawing this picture. I'll just justify it like that. And then finally, what's the chance that x is exceeds t plus s? This is 1 minus the CDF of x evaluated at t plus s, right? And then the bottom, similarly, will be 1 minus the CDF of that exponential evaluated at t. Okay, so and in fact, you know, really, I need all this. This is for t and s greater than 0, right? This is for t and s at least 0. Okay, so if I make that assumption, then I don't have to worry about the indicator function stuff. So let's see, what is this then? It's just going to be 1 minus quantity, 1 minus e to the negative lambda t plus s over 1 minus e to the negative lambda t, right? And all that boils down to e to the negative lambda t plus s over e to the negative lambda t, which, and hey, guess what? This cancels with that, I guess, right? So the final answer is just e to the negative lambda s, which is, in fact, the probability that x exceeds s. Very, very special and important. You have to know this.